Hello everyone, my name is Yogesh Yapunia, and today in this episode we are going to continue our journey in the world of static charges. If you remember, in the last episode what we discussed was how the two charges at rest will attract the other negative charge if it is a positive one, or how the first charge, which is a negative one, will repel the other negative charge. But actually this is all about the qualitative measurement or the qualitative aspect of the charges at rest. Just imagine what would be the quantitative aspect. Well, what do you understand by the quantitative aspect is that to what extent can a charge go to affect the other charge, and the same from that charge point of view also. This was a very tricky question and Coulomb tried to answer this question. He said, okay, the extent to which a charge can affect the other one can only be calculated or can be seen if I have two charges interacting with each other, and if I can somehow find a way to the force that is acting between the two charges. And then he made a very simple experimental setup that you all can make at your home also. What you all need is nothing but just two plastic spheres. Well, make sure that you have got a plastic sphere or any other insulator material that can be charged so that you can see the effect. For example, if I consider this pen as a charged sphere, where this point is a charged sphere and this point is a charged sphere, you have to make sure that it is joined by some sort of conducting material. Well, if you don't want to say that I don't want to use the insulators, you can even use the metal spheres, but make sure that they are really very light, or the hollow spheres. Now, following the experimental setup that was used by Coulomb, we can have the one at our home also, and how it is possible. For example, if I consider this pen as the experimental setup part, that is, if I have got two spheres, one at this point and one at this point, and if I join them by a metal rod, well, actually the rod has to be really very thin so that it can support here. What I am going to do now is, if I place some uncharged sphere, that is, if I place some uncharged sphere here with respect to this sphere which is charged, what will happen is that there will be some transfer of charge from this charged sphere to the charged sphere that I have got here. So when Coulomb tried to do this experiment, what he found was that if he has got a charge, say Q, and after bringing the uncharged sphere near the one of the charge Q, he found that the charge was evenly distributed. Do you know the reason? Yeah, you know it, because whatever the metal spheres we were using, they were conductors. So what they will do is, if they come in contact with any other metal sphere or any other metal body, the redistribution of charges will take place, and that's why Q becomes Q by 2 and Q by 2. Now, if you go on further, you can even achieve a situation where the charge can be Q by 4, Q by 4, and so on. So one thing was really clear to Coulomb, that the force of that was acting between the two charged spheres was proportional to the charge of individual spheres. Okay, so you are not agreeing with this. I will tell you how it happens. Now, if I use an experimental setup to prove the point that I was talking to you, then I have this experimental setup. I have got this hollow cylinder and I have got some sort of cube-like structure. Well, make sure that it is covered by a plastic polythene that is transparent to you. Now, what you have to do is, for example, you can just simply take a woolen wire or a woolen thread so that you can connect this upper portion of this cylinder to the experimental setup part A that you have considered, that is the charged spheres. Now, you have to bring an uncharged sphere here with respect to the discharged sphere. So what Coulomb saw, that the charge Q on this sphere got redistributed, and both these spheres, they got the charge Q by 2 and Q by 2. But there was one more thing to come. When Coulomb found that if I am considering the distance between the two charged spheres and if I change them, Coulomb said, I saw that force was decreasing. Means he saw that if I reduce the distance between the two spheres by half, the force becomes 4 times, and if he doubles the distance, the force became 1/4. So two things were crystal clear. The crystal clear things were that the force that the spheres were acting upon the other one was clearly proportional to the magnitude of the two charges, means how much are the two charges there. That is, if they are q by 2 and q by 2, the force is proportional to those charges. And the second thing was that the force varied inversely with respect to the distance between the two spheres. That is, if the distance is increased, the force becomes smaller, just like some sort of square root or something. So after formulating these things, Coulomb gave us some results that we will study now. Now after we have done what Coulomb did so many years back, what we found? We found that the force between the two charges was dependent upon the magnitude of the two charges. That is, if you change the magnitude of the charges, the force changed. And the second thing was that the change in the distance between the two charges that we have considered resulted in the change in the force acting between them. So what we have got? We have got that F, that is the Coulomb's force, is proportional to the magnitude of the two charges, where I have considered q1 as the magnitude of the charge 1 and q2 as the magnitude of the charge 2. Also, the force F is inversely proportional to the square of the distance between the two charges. Here I have considered r square as the square of the distance between the two charges. Now with the help of this 1 and equation 2, what I get is that F is proportional to q1 q2 by r square. So in order to remove this proportionality constant, I have to insert something there, and what Coulomb found that it was equal to 1 by 4 pi epsilon naught. Yes, so the Coulomb force became F is equal to 1 by 4 pi epsilon naught times q1 q2 by r square. Well, it looks to be really very simple formula, but one thing we should pay attention to it. The epsilon naught term is known as the permittivity of free space or vacuum. Well, what exactly permittivity is that, suppose if I have got some certain place, and if I place two charges, say A and B, in that place, for example, if I take that in my room, so there is some air. So Coulomb said that since the two charges will interact and they will exert some force on each other, the resistance will be provided by the medium into which they are kept. And he said that with the change in medium, the value of epsilon naught will change. And that is why he said that if I consider the two spheres or the two charges kept in vacuum, epsilon naught will be the value of the resistance offered by the vacuum. If I change into some other medium, the value of epsilon naught will become epsilon, and that epsilon will be the relative permittivity of that medium with respect to vacuum. Now what we have discussed in our earlier classes is that force is a vector quantity. I am right? Yeah, because force means something that you have got a mass that is in some particular direction, that is accelerated. That means force should be a vector quantity with a particular direction. Now if I have got the two charges, say q1 and q2, and if I am standing at point O and observing the two charges, what I will see that the position or the distance between the charge q1 and the point O is, say, r1, and the distance between the point O of my observation and charge q2 is, say, r2, then I will be able to know how much force the charge q2 will be exerting on the charge q1. But there is something missing, and the something that is missing is that the direction. We must not forget that force, being a vector, should have a direction of it, that is, in which direction it is acting. Now if I consider that I wanted to know how much force the charge Q2 is pressurizing or having upon the charge Q1, then what will I simply get is that I have an 1 by 4 pi epsilon naught times the magnitude of the two charges Q1 and Q2 divided by the magnitude of the distance between the two charges, say R21. But what I have to consider here is the unit vector. Yes, the unit vector is really very important. It will give me the direction of the force acting here. So if I say F21 is 1 by 4 pi epsilon naught times Q1 Q2 by R21 square times unit vector of R21. This is equation number 1. If I go the other way around and I say what is the force on 1 due to 2, then I will go for F12. There will not be any change except for the fact that the only change will occur in the unit vector and its direction. So I will have here 1 by 4 pi epsilon naught times Q1 Q2 by R12 square times the unit vector of the direction, that is R12. With these two equations you can see something, that is the unit vector R12 is equal to the negative of the R21, that is they point in the opposite direction. If I have got this pen and if I say that this tip is, say, suppose Q1 and this end is, say, suppose Q2, so this tip, the force exerted will be in this direction, and if I consider from this tip, the force exerted will be in this direction. Here I am only considering that one of the charge is positive and negative. If I say that both of them are positive, then the force from here on this point will exert in this direction, and this will exert on this in this direction. So what will happen? You can clearly see that the direction is totally opposite. Do you find something new here? No. What you simply find is that F21 is equal to the negative of F12. What is this? Yes, this is the Newton's law of motion, the third law. For every action there is equal and opposite reaction. So here we got something very familiar to us but was hidden in the world of electrostatics. So now what we have considered here is, I have considered a charge 1 and 2. I knew about how they will interact with each other. If they both of them are positive, they will repel, negative, they will repel. One is positive, other one is negative, they will attract each other. But then we found out how Coulomb devised a method to know about the quantitative aspect of dealing with the force that one will act on the other charge. And then we came to know how these forces come into existence, and that means the mathematical analysis of the Coulomb's force. We also came to know about the vector notation of the Coulomb's force, because the force being a vector should have some direction. And then we found out that whatever the Coulomb force that we are studying right now in electrostatics is nothing but something that we saw earlier in our Newtonian mechanics, or you say the classical mechanics, that is for every action there is equal and opposite reaction. I have got a very good homework for you. Well, we have seen that for every action there is equal and opposite reaction, the third law. Can you simply find out the second and first law if possible? I am saying if possible, that does not mean it is not there or it is there. You have to find it out. Can you find out the first and the second law that are in disguised there in the Coulomb's law of forces? And if you can, you are most welcome to make something. In the next episode, we shall be discussing the concept of electric field. What is an electric field exactly? How does it affect the charges present in the vicinity of some other charge? And then we will know the more depths in this world of electrostatics. Thank you.